In order for us to do part 1, we need to make use of a concept that we have learned in our secondary school. In our secondary school, we have learned that for any line, for example, y is equal to mx plus c, there is a relationship between m, which is the gradient of the line, and the angle that the line makes with the positive x-axis, which means that we are talking about this angle here. I'm going to call it theta. And m is equal to tangent theta. This was what we have learned in our secondary school. So what we are going to try do now is we are going to make use of this concept, and we are going to assume a line with gradient of m1, and I'm going to let this gradient m1 be 2, so it will have a positive gradient, and this line, the gradient is equal to 2. So the angle that it makes with the positive x-axis is going to be this angle here, and we are going to call it theta 1. So according to what we have discussed, tangent of theta 1, this is equal to 2, which means that theta 1 is equal to tangent inverse 2. We're going to do the same thing for another line, which according to what the question hints to us, this other line should have a gradient of minus half. So minus half is a line with a negative gradient. So this line, let's say m2. So the gradient is minus half, and the angle it makes with the positive x-axis is going to be this angle here. It is going to be an obtuse angle. This is theta 2. So tangent of theta 2, this is equal to minus half, which means that for theta 2, since tangent of an angle is minus half and we are working on an angle that is in the second quadrant, so this must be pi minus away the basic angle, which is tangent inverse of positive half. And we can also rewrite this as pi, this negative. I can sort of like bring it into the tangent inverse, so it will become plus then tangent inverse of minus half. So we are having two lines where we can see that m1 times m2 is going to be 2 times minus half. This is equal to minus 1. So when the gradient of two lines are multiplied together and we get a minus 1, this tells me that for the two lines, let's say this is L1, let's say this is L2, we can say that L1 is going to be perpendicular to L2, which means that if I were to draw the two lines together, let's say L1 is here. So this is, let's say, our L1, and L2, for example, is this. So this is our L2. Since they are perpendicular to each other, that means this angle here must be 90 degrees. And if once again we reference this to the angle that both lines makes with the positive x-axis, we are talking about this, which is theta 1, and this angle here is theta 2. So theta 2 minus away theta 1, this is going to be equal to 90 degrees or half pi. Theta 2 is pi plus tangent inverse of minus half. So this is theta 2. As for theta 1 is tangent inverse of 2. So here let's go for a tangent inverse of 2. This is equal to half pi. So if I were to rearrange this, bringing tangent inverse 2 over to the right hand side, we will have a positive tangent inverse 2. This, if I were to bring it over to the right hand side, it will be minus tangent inverse of minus half. So this, if I were to bring over to the left hand side, we will have a pi minus half pi, which gives us a half pi. And this will explain to us the equation that the question is asking us for. And in part 2, we are supposed to be discussing about the intersections between C1 and C2. So to do that algebraically, let's solve this as a pair of simultaneous equations. So I'm going to let this be equation number 1, and I'll let this be equation number 2. Solving them simultaneously by letting equation number 1 be equation number 2, we will have a 1 over x squared plus 1 is equal to k over 3x plus 4. cross multiplying 3x plus 4. This is equal to kx squared plus k. And bring everything over to the right hand side. This will be kx squared minus 3x plus k minus 4. This is the term that is independent of x. So we now derive a quadratic equation, and according to the question, since this curve C1 and C2, they are going to experience intersections, that means that for this quadratic equation that we have derived, it is going to have solutions. So we're going to make use of discriminant. In fact, I'm going to be letting the discriminant be bigger or equal to 0 so that I will have solutions to this quadratic equation. So b squared minus 4ac, or let this be bigger or equal to 0. Simplifying and bringing everything over to the right hand side so that I can have a positive coefficient for k squared. That is my own personal habit. I just like to make the coefficient of the highest power be positive. So bring everything over to the right hand side, we will have a 4k squared minus 16k minus 9. This is going to be less than or equal to 0. Factorizing this, we will have a 2k plus 1 and a 2k minus 9. This is less than or equal to 0. On my number line, we have a minus half and a 9 over 2. And this is a number line with respect to k. If I were to plug a number that is bigger than 9 over 2 into this entire expression, I'm going to get a positive number. Something that is in between will give me a negative number, and then a negative, and then a positive number. So we are looking for k such that this thing is going to be less than or equal to 0. So I know k is going to be bigger or equal to minus half, and less than or equal to 9 over 2. So the set of value of k will be k belonging to any real numbers such that k is bigger or equal to minus half, less than or equal to 9 over 2. And part 3 here is pretty straightforward. We are supposed to sketch the two curves when k is given to us as 2. So for this curve, from my graphing calculator, this is what I have obtained. Something to take note of is that for this curve, as x tends to plus or minus infinity, y will tend to 0. So it has a horizontal asymptote of y is equal to 0 for this curve. As for this, when x tends to plus or minus infinity, y will also tend to 0. So for the blue colored graph that you see here, it represents C2, where it also tends to the horizontal asymptote y is equal to 0. And at the same time, when x is equal to minus 4 over 3, it's going to cause the denominator to be 0. So x is equal to minus 4 over 3 is going to be the vertical asymptote for the curve C2. And as for the rest, I guess we can just press them into the calculator, getting the intersections between the two graphs. The coordinates are this. And here we are supposed to find the area of the region that is bounded by C1 and C2, which is actually going to be this region here. So to calculate the area, we are going to make use of integration. And we are going to be integrating from the x coordinate of the intersection here, which is minus half, to the x coordinate of the intersection here, which is 2. C1, so 1 over x squared plus 1, minus away the equation of C2, which is 2 over 3x plus 4. So for this, when I integrate it, it is going to be tangent inverse x. As for this, it is minus 2 over the coefficient of x, which is 3, and ln modulus of 3x plus 4. So from minus half to 2. Let's substitute this in. We will have a tangent inverse 2 minus 2 over 3 ln of substituting 2 in 2 times 3 times 2, 6 plus 4, this is 10. So we'll have this minus away tangent inverse of minus half minus 2 over 3 ln of substituting minus half in. This is going to be equal to 5 over 2. And if I were to combine this and this together, isn't it familiar? tangent inverse 2 minus tangent inverse of minus half. This was actually what we have explained in part 1 of the question, which means that for this, it is going to end up with a half pi. Then I'm going to go for this and this, which is plus 2 over 3 ln of 5 over 2 minus away 2 over 3 ln of 10, which we can combine them together. It will become 2 over 3 ln of 5 over 2 divided by 10. So let's do a quick simplification to this. This is equal to half pi plus 2 over 3 ln of this is equal to 1/4, which we can definitely rewrite this 1/4 as 2 to the power of minus 2. So minus 2, if I were to bring it forward, my simplified version is going to be minus 4 over 3 of ln 2.